this video, I want to talk a bit about relative and dependent motion, so as two separate things. However, both of these things more or less describe how we might conceptualize and mathematically describe the relationship between the motion of two different objects that are both themselves moving. So if I look at a simple sense of one-dimensional translation, let's define a point we'll call 0, just our datum or our 0 point on the right, and we'll define the location of two particles, which I'm going to separate a little bit here just to be able to draw between them. And we'll define particle A as having a position xa and particle B having a position represented by vector xb. So these two particles are moving, and here we're defining their position with these vectors labeled x. We can also, though, define the position of particle B with respect to particle A by drawing a vector between those two. Now in this case, this would have a unique label because it's a different measurement, and typically how I would write this is that it is the position of B relative to, using a slash, particle A. So I'm saying it's the position of B relative to A, written in that way. Now using vector math, vector addition, we could write these things out, these vectors out as equations. So I can say that xb is equal to xa plus xb slash a. Similarly, I could rearrange this equation and describe the relative vector b slash a as the difference between xb and xa. Now for me, I always remember this, the order of these things by saying, okay, it's b slash a, which means it's going to be b minus a. And that way I can always kind of keep it straight in my head when I'm trying to write it out. Now, I can take a time derivative of these things and express these same quantities, but now in terms of velocity, using the same ordering and notation. So what this last equation here is saying is that the velocity of particle B with respect to the velocity of particle A is going to be the difference between their two velocities, right? And that should make sense intuitively, and especially in a one-dimensional situation where we're only traveling one direction, that should make pretty good sense. But it can get more complicated to think about, and that's why sometimes it's nice to be able to fall back on this mathematics in order to be able to represent the situation. Similarly, I could take another time derivative and write all of these same equations in terms of acceleration as vector additions in the same way. Oops, I did that incorrectly. There we go. And that can be particularly useful then for analyzing how things are moving relative to one another. Now, of course, I drew a one-dimensional case on here, but it could have just as easily been two particles located at different locations, moving in completely different directions. So for example, let's call this one A and this one B, and let's say this one's moving this direction and this one's moving this direction, which we would call, let's say, v velocity A and velocity B, I could figure out what the relative velocity is between these two, again, by expressing it in terms of this vector quantity as the difference between them. So I could subtract those and write those out. And that can be particularly useful in that it's not constrained to this one-dimensional scenario that I first presented. The other piece of this then is thinking about when the motion of these two things is dependent on each other. So in this first example here with the A and B particles, in theory that they might be completely independent, right? One can move in any direction it wants and the other can move in another direction without really influencing each other. However, in some cases, we have scenarios where those things are not true and that they are dependent on each other, and that can give us some useful information. So a simple example is two blocks, 1 and 2, where they are connected by a rope which passes over a pulley like that. And therefore, any velocity, let's call it v1, of block 1 must directly influence the velocity v2 of the second block. So this one might be pretty straightforward, but we can look at this using a method that's somewhat useful, and that is to refer to it as position, or in terms of position. So for example, I could take and define this pulley as that's my datum point, my 0 point, because it's not itself moving. And therefore, the rope, which wraps around from 1 to 2, is going to be some constant length, right? So let's go ahead and label that. The rope from here, wrapped around the pulley to here, is going to have some length, let's call it L. And therefore, if I take that and say there's some length L, it's going to be equal to, let's call this distance S1, and this distance S2, corresponding to blocks 1 and 2 respectively. Then this length is equal to S1 plus S2, and there's some little bit of rope in between here, which never changes length. It's within these two datum lines that I've drawn for the pulley. So let's just ignore that for now. If I take the derivative of these positions in order to get velocity, the derivative of this constant L is 0, time derivative. And the derivative of S1 is V1, and the derivative of S2 is V2. And therefore, I get a relationship that V1 equals minus V2. And really, this negative sign, all this really indicates is that they're kind of moving in opposite directions. One's moving up and it causes the other one to move down, and that kind of comes out of that. And really the reason that happens is because S1 and S2, if one is increasing, then the other by default has to be decreasing. Now, we could look at this in a slightly, not much, but slightly more complicated pulley scenario, in that suppose I have a pulley here and I have a block 1 here. This wraps around, and let's see, I'm going to erase this. And I have a rope here which wraps around another pulley, or excuse me, this pulley wraps around another pulley. And it attaches here to the center of this one. And this second block hangs from the second pulley. So now, suppose I have a velocity v1 and a resulting velocity v2. And I want to better understand what's happening in this scenario. Well, again, I can do the same sort of analysis that I had up here, where I define that there is some total length of rope. My pulleys, only one of them is not moving. That's this one up top. The bottom one moves up and down. So this top one can be my datum, or my zero line. And therefore, I'm going to define S1 for pulley 1, and then I'm going to define S2 for pulley 2. And one thing that we can see is that these two sections of rope in here, while they do change length, both could be defined by S2. So therefore, I have S1 plus 2 S2 equals L. And this again neglects the amount of rope that's wrapped around the pulleys, but since that doesn't change it, it doesn't really influence our answer. So again, if I take a derivative, I get 0 equals v1 plus 2v2, and I can solve this and say that v1 equals minus 2v2. So what I would find in this case then is that v1 is going to be traveling twice as fast as v2, and they're traveling in the opposite directions based on my positions here. Now, of course, this isn't this idea of dependent motion and even relative motion, it isn't limited to these pulley type problems. I could define a number of things. One that I like, because it kind of makes sense to me, is a piston in a cylinder. So suppose I have a piston in a cylinder, and attached to it is a crank arm, and that's attached to a shaft, which itself is rotating around a fixed point. So I have some sort of rotation occurring here, and that yields a motion of my piston up and down within the cylinder. So this is another example of a dependent motion, in that I have a rotational motion down here leading to a translational motion up here, and those two things are rigidly coupled together, which means we can't separate them, but we can use that mechanical linkage in order to describe what's happening between the two, and kind of eliminate some of our unknowns if we were to try to solve this problem. All right, thank you.